In this lesson, we're going to go back to kind of where we started the last lesson and just get more into graphs of exponential functions and their inverses, which are logarithmic functions. So we're starting out with a graph of y equals 2 to the x. I'm going to fill out a table for it. You could get this off your calculator, but we want to think about where it comes from. I made the table kind of have one more cell than I wanted, but that's fine. So we're just going to fill in this table for these common x values. Instead of going -2 to 2, I'm going to go -2 to 3 because I have an extra spot. So the bottom of the table is kind of easier to think about, like 2 to the first power, when I plug in a 1 is 2. 2 to the second power is 4. So this graph is just basically our outputs or powers of 2. 2 to the 0 we know is 1. And 2 to the -1, that means, just right on the side, 2 to the -1 means 1 over 2. So this is going to be 1/2 here. And this one, 1 over 2 squared, is 1/4. So when I graph that, I'm going to start from the whole numbers. So 0, 1, 1, 2, 2, 4, 4, 8, and then over here, the graph kind of tails off this way. Probably should be a little lower. It's a little hard to graph on the video, but we'll talk more about it when we get there. So that's your graph of y equals 2 to the x. Now there's two ways to think about it. We're going to find the equation for the inverse first. Actually, we're going to find that second. We could define the inverse graph, just take our table and switch the x's and y's, because we know inverse means switch x and y. So for example, if I have the point -2 1/4 in my original function, the point 1/4 -2 will be on my inverse. So I'm just going to actually switch x and y's first and do the graph, and we're kind of going a little bit out of order, and then we'll go back and find the equation. So I have 2, 1, and 4, 2. So again, we're just switching these values, so 8, 3. So if I go and graph this one, I'm going to start out with that 1, 0, and then 2, 1, and 4, 2. And this is a little bit off, but we'll put this point out here. And then these points kind of fall in here, and we get a graph that looks like this. So we don't have its equation yet. The actual grid is not really symmetrical, so it's kind of hard to see. But if we did the draw on that line y equals x, right, that line running through the origin with a slope of 1, we would see that that flips over. So finding the inverse, I'm going to do down here. So I'm going to take my equation, and I'm going to switch x and y. And we know that there's no way to solve for that y unless we put this equation in log form. So we know when we write a logarithm, we write log. The base goes here. We know the exponent's the answer, and the number it was equal to goes here. So the inverse function is log base 2 of x. So I'll write that on the grid here, or the graph, y equals log base 2 of x. Now there is a way to directly graph it on your calculator. I'm not going to put it in this video. Your teacher might show you in school, but the idea is that it's just switching the x and y's from the exponential equation to get to the log equation. So the next thing we're going to look at is the qualities of these graphs. Now this is going to be a little tricky to show the whole thing when I move this up. Okay, so I had to move the background separate from the writing, so it's not perfect, but I think I have it decent enough to talk about the questions. So first off, we're going to talk about domain and range. I'm going to look at 2 to the x first. So the domain of 2 to the x, remember domain is where it goes back and forth. This side goes back forever, and even though this is mostly going up, it is going forward forever. So our domain is all reals, or -infinity to infinity. Our range is where the graph goes up and down, or in the y direction. And this is our first time we're really seeing this happen. There is no open circle, but if I'm going up along the page, there's no graph down here for the red graph, the 2 to the x graph, And it will never, if I think about these fractions, which got moved a little bit, I'm just going to keep getting smaller and smaller fractions, but I'm never going to hit 0. So I'm going to get 1/8 and then 1/16 and 1/32 and 1/64. And you can see they just keep getting smaller and smaller, but won't touch 0. So the way we denote that is they start right after 0. We show that with parentheses versus a bracket, which would say equal to 0. And then this side of the graph we see goes up to infinity. If we look at the log graph for domain and range, the log graph has the same situation for the x's. So we see that it starts right after the y-axis or right after 0. And then this side of it goes to infinity. Now it should make sense that the range from the 2 to the x graph would match the domain from the log base 2 of x graph because they're inverses. So they're x's and y's, domains and range switch. The range of that graph we should expect to be negative infinity to infinity, and we do see that this arrow goes down, that one goes up, so it's negative infinity to infinity. What point do these graphs always include? So if we start to think about it, since anything to the 0 power is 1, any parent exponential function is going to include the point 0, 1, because if I raise whatever the base is to 0, I'm going to get 1. Switching the x and y for a log graph, a parent logarithmic graph, log base 2 of, or log base b of x, whatever the base is going to include the x and y switched point, so 1, 0. We have a new term to talk about, something called an asymptote. Whenever we have these graphs going towards something but not touching it, so for example, the exponential graph is going towards the x-axis on this side, but it will never touch it. It keeps getting closer and closer. In math, we call that an asymptote. In this case, it's a horizontal asymptote. So the equation of that line, the equation of the x-axis is y equals 0. That's the technical correct answer. I can write the x-axis, right, is another way I could think of that. For the log graph heads towards but never touches the y-axis. And the equation of the y-axis is x equals 0. So that graph has a vertical asymptote, an up and down line that it does not touch. Kind of related to those two are end behavior, and it's been a little while since we've done end behavior. So end behavior talks about where the graph goes in each direction. So if I look at the left side of my exponential graph, I'm just going to go over it in black. I know it's kind of messy up here with moving the writing and just all the stuff I've already written. So as I look towards this side, we know as we go back that the x value is heading towards negative infinity. So as x goes towards negative infinity, where does the y value go? Well, the y value is heading towards that line y equals 0. So y is heading towards 0. If I go in the other direction, if I go towards positive infinity, on this side of the graph, both the x and the y values are going towards positive infinity. So the end behavior on the left side, as x goes back to negative infinity, y doesn't go to negative infinity, it only goes towards 0. It doesn't get there, doesn't touch it, but it goes towards it. In the other direction, both are going towards positive infinity. Now here I have to move this up. My graphs might move slightly. Oh, they are. Everything but the log table is in place, is staying now. So looking at the log graph, on the left side, this side, x actually doesn't get to go back to infinity, negative infinity, like it did with all of our polynomial graphs. X, the furthest it can go back, it's heading back towards 0, right? X equals 0. And the y is going down to negative infinity. In the positive direction, both sides are heading towards positive infinity. Now, something about log graphs is they're super slow in terms of their y. So you'll see it's going up slower and slower and slower, just like the exponential equation is going up faster and faster and faster. Its slope is increasing by a lot. The log graph is actually going up slower and slower and slower, but it does continue to always go up a little bit by little bit, so we still say that its y goes towards positive infinity.